Hello, my name is Quinn Lathrop, and my presentation today is called Let the Product Lead, R&D Paradigms for Recognition Models of Handwritten Math Expressions. I'm recording this on a Wednesday evening in Denver, Colorado, and like a lot of things over the last 6 months, I think this is the first time that I've pre-recorded a presentation in this way. Obviously in my apartment right now, and hopefully we'll be able to keep the background noise and the dog to a minimum, but we'll see. To start off, I'd like to explain a little bit about the organization that I'm a part of. So I'm part of an organization called AI Products and Solutions, which is inside of Pearson. We are a global organization. We have a branch of the team in Poznan. My group is based in Denver, Colorado, and we're spread out across the US and across the globe as well. We cover research, development, engineering, product, design, and we own products and AI features and capabilities all the way from ideation on a whiteboard to delivery in the hands of users. We do this in order to achieve broad innovation goals that are set by Pearson by developing these customer products first. And so we achieve innovation by developing product features. The work that I'm going to talk about today has spanned many months to develop the capability and get it to the state where it is. And there have been so many contributors to this work, including some of our team members that are based in Poznan. Now, my personal connection to the AI Products and Solutions group in Poznan spans several years, and actually 2 years ago, my wife and I were able to visit. It was right towards the end of November. We were able to go to a Christmas market. We had some amazing food, and probably the most interesting cultural experiences in this bottom right, where we happened to be there on Black Friday. And I did not know that was a global cultural experience, but that was certainly interesting to be in a mall in Poland on Black Friday. One thing that I have picked up during the past 6 months during this work from home period is baking with sourdough, and I've tried to spread that as much as I can among the team by creating a Slack channel, which is #everythingissourdough. These are some of the photos that I've posted over the last several months. Did not know about any of this before needing to spend a lot of time at home and learning how to pick up some new skills, but I certainly enjoyed it, and I've been really enjoying connecting with members on the team through these new means. So getting back to the topic at hand, the product that our group developed and launched towards the end of last year is called Ada Calculus. It's available on the Apple iTunes App Store, iOS. The typical flow, or the flow that at least is important for this talk, is what we call internally check this problem. In check this problem, a student brings a problem that they are working on in the normal course of their calculus class to the app. They typically take a picture of their work. We translate their picture of the work into LaTeX or some other form of computer readable math. The student receives step-by-step feedback on what they did, and then we offer them personalized hints and tutoring, specifically through reinforcement learning recommenders. Now, I'm going to show just a quick 1-minute video that is a marketing video at its core, but it helps show some of the screens and some of the usage, and I'll just narrate over it. And so the typical use case is, again, as a student, you're working on your homework, you are struggling to get the right answer, you're stuck on something. Oh, Ada as a calculus tutor is right there. You can take a picture of your homework. We will then score it step by step, and then where you get a step wrong, we offer hints and very specific either videos or other content to help you through your problem. We also have more conceptual videos such as this that's showing the mass of a black hole. And the goal is that this product is not tied to any one specific course, but that it is a tutor that is with you throughout your course in whatever calculus class you're going through. So that's a quick rundown of ADA. Now, specifically what we're talking about is handwriting recognition of math expressions. And so just to be set the context as clearly as possible, the goal is to receive an image, such as the image of the line paper with the math expression. And then we have some model that turns that into, in our case, specifically LaTeX. Now, there's a few noticeable challenges in this. One is the complexity of math, especially as we get into more complex algebra or even more complex calculus. We have structures of fractions, of integrals. The typical a typical expression of math is not necessarily read left to right. Another interesting challenge is that LaTeX communicates that structure of math with invisible characters. And so, for example, we have in the second set of parentheses x squared. That exponent is communicated through a caret, and we see this throughout the LaTeX representation of math. There are structures communicated through invisible tokens, groupings communicated through brackets that are not rendered. And so this is a particularly challenging modeling problem that has been obviously not novel. There are several ongoing competitions and obviously competitors to this to Ada calculus in terms of handwriting recognition models. But as any kind of product feature that has this problem, the core issue tends to come down to data. So a typical flow is that first you collect data and then you iterate on your model. This is in a sense a bit waterfall-like, where initially the emphasis is on collecting a sufficient amount of data with sufficient scope, and then when we have the data, we consider that data set fixed for some period of time and iterate on the model in order to improve performance on that data. What's challenging about this, and we'll go into more, but just to start off with, is that because it is a sequential waterfall approach, it is very difficult to iterate on how you collect data at the same time that you're iterating on the model itself. And part of that is just the amount of time that it takes, how you're collecting the data. If it's through some manual process, such as this picture of a table where you can go to a college campus and try to get actual calculus students to write down math, it can be expensive, it can be time consuming, and in general, it's just a sizable task. The other interesting thing is that even if you do that manual data collection, whether it be through an actual calculus college student or through some other farm like MTurk style of collecting data, it doesn't mean that it's perfect. And I grabbed this example because I think it's very interesting in that you see how this v to 0 is not in a straight line. And if you notice, the exponent to the secant has an unusual amount of space in between it. To me, this reads like somebody that wrote down a calculus expression but had no understanding of what they were writing down. And those qualities and characteristics can come through and can be a dramatic difference between a data collection effort and what you actually see live on the product. So our approach is a little bit different. What the strategy that we've taken is to iteratively build a synthetic generation capability that aims towards specific requirements. And those requirements can iteratively change over time, and the capability can iteratively change over time. What this gives us is exact control over the distributions of the math expressions, the characters, the locations of those characters, any visual qualities of the math, noises around the image, simulating the photo, as well as any augmentations can be made directly. We've gotten to the point where we can have exact control over every pixel of the image. And because we have a capability rather than a data collection effort, we can create millions of 100% perfectly labeled images in a matter of hours. What this then enables is the flow on the right, where we have this pipeline, we can train a model, we can evaluate a model, and then have an immediate feedback loop that can either, as typically happens, inform model training or model iteration. But more importantly, we've shortened the cycle of going back and changing something about the data generation in order to do a model training and a model evaluation. Where if a large-scale data collection effort collecting hundreds of thousands or millions of images could take 6 months in the past, we can do this complete cycle in a matter of days. And so let's get a little bit more specific with the example that I showed earlier. And so here's the image. And of course, the goal of the model is to extract this math expression and to do it correctly. But to do so, the model needs to be able to undo all the other features of the image. It needs to be able to see that certain lines and colors are part of the background, that certain marks are not part of the target expression, but are just involved in the image itself. There could be what we call bleed-throughs or erasure marks. And this is just an overall challenge to the complexity of the problem. Our synthetic data can reverse this process by building up these same features in the other direction. So we start with the math expression, the target math expression. We then render it in some font with some writing utensil and some color with some characteristics. Each character can have specific distortions or augmentations to mimic how, for example, in this image, the right parens are slightly different and the left parens are slightly different, even though it's the same person writing the expression. We can then impose a variety of backgrounds, add whatever visual noise we would like, and then simulate a photo from a certain angle, distance, fuzziness, whether there are shadows. And this helps us create images that are fairly close to what we expect to see from students taking images of their handwritten calculus work. And so, for example, here's a slide of images, and I'll just wait a few seconds and give everyone a chance to look through this and try to pick out which of these images are synthetically generated versus the ones that are actual pictures of math that a human wrote. And you can tell there are characteristics that become obvious the longer that you look at it. But the point is that we're getting very close, if not being able to pass some of this test. So here, every image that's surrounded by that red box is synthetically generated, and everyone that's not is a real image. So what are some benefits to this? Well, number one is that we can follow product development life cycles very closely. If you recall from the user flow in the video that I showed earlier about Ada Calculus, the handwriting recognition model is the entry point for other downstream capabilities. And so it's important that we are able to integrate early and often that capability while we're developing the downstream capabilities so that we can understand how they work and give enough time to iterate on them. And so, for example, by synthetically generating data, we can iteratively build along with these development cycles. So say for alpha, maybe we only cover one font, this perfect print font, and we only cover black and white. For beta, we now have the capability where we can still do fonts and still do the math, but not in a full color image. And then when we get to MVP, then we can take on the full scope of something that actually looks like an image. This removes, or is a very different way to a lot of other deep learning approaches where there's kind of a mystery behind it, or at least a perceived mystery behind it, of there's this black box. It's hard to tell when exactly it'll work and when it won't, but as long as we just give it enough data, things will just work out eventually. This breaks that down by understanding what the final goal is, but starting small and iteratively building up towards that North Star. Another benefit is that we have exact control and visibility into the distributions, the population distributions of our training data in whatever dimension we care about. And so, for example, this is showing some token distributions in the table, as well as image height and width in pixels, so that we can understand the ratio of and the size of the images coming in. What this allows us to do is collect data on the app, see what's actually coming in, compare, for example, with the image ratios, compare the image ratios that are coming in from the device from what the model was actually trained on, and we can then modify the training population distribution of image ratios to perfectly match either what has come in on the app or what we expect to come in to the app at some future date but hasn't happened yet. And that ability to have control both in a reactionary way as well as a forward-looking way is incredibly powerful when we're doing this capability development inside of product development. Another benefit is that the user behavior can drive our backlog and our priorities. And so one example is that computer screens, if you take a picture of it with your cell phone, and you could try it right now, oftentimes will produce these very dramatic artifacts. And so, for example, we get these grid lines, we get these waves, and if a model has not been trained on these, if a computer vision model has not been trained on these, if it's only been trained on pieces of paper, for example, these can cause hallucinations. And that could be a challenge. Now, if we had followed kind of the typical ML development flow and started seeing these images coming in on the app, and our model wasn't performing as well on these computer screen images, we would need to start a new data collection effort of trying to gather these computer screen backgrounds images. If that cycle takes another 6 months, that's 6 months that we are not improving our users' experience on the product. And so instead, what we can do with our data generation capability is very quickly generate images that have this as a background feature, just as we have some that have graph paper, lined paper, or shadows, and very quickly ask, can our model architecture, can our existing infrastructure support this expansion in scope? And then if so, we can very quickly size up and prioritize what it would take for the product to also be able to perform at a reasonable level with these kinds of images. That gives immense power to our product team to be able to prioritize against other priorities and appropriately allocate our resources and our development efforts with the user's experience at top of our mind. And a final benefit is in modeling. Because we have 100% correct pixel level tagging, we have access, at least from the computer vision side, to a range of object detection models. The difficulty of tagging LaTeX versus tagging bounding boxes versus tagging pixel level masks come at exactly the same cost with our capability. Where if we were doing this through, say, mTurk, it would be much easier to pay for someone just to tag the LaTeX than it would be to tag boxes or to draw masks on top of all of these. And so this is an example of a mask RCNN model that is predicting on this, and so you see the masks drawn on top of these images, and you can see what the model picks out as important. And so those are the benefits. The last slide that I would like to show is that we have open sourced a data set on Kaggle that has 100,000 of these images. I'm going to go to this link, and I'll leave up this link after I finish in the Q&A if anybody wants to jot it down. But this is the data set. It's available open source. The description covers a lot of the same content in this talk. And if I'll just jump down to some of these examples, what we have obviously are the images themselves in various, 100,000 of them. And then we also have the ground truth JSON. And what I just wanted to show is that to kind of drill in the part about how much tagging and the pixel level tagging that's available here is here we have the string of ground truth latex, so lim, u to the 7, cotant, etc. And down in this image data block, we have both the list of LaTeX characters, the list of only visible LaTeX characters, and then connected to those visible LaTeX characters are the coordinates of the bounding boxes, the relative and the raw bounding boxes, as well as this PNG masks where this first element is the mask for the first token, which was a limit token. If you have not worked with this data before, certainly there's a lot of object detection tutorials that'll show you how to turn these into, for example, TF records. But we also provide some starter notebooks for those that are new to working with this data. And so, for example, in this Visualizing Ground Truth JSONs notebook, we bring in some of that data and convert the masks to actual visual pixels, and then provide an example of how that can be done. And so, for example, here is a synthetic image, and then here is that image with the ground truth overlaid in LaTeX tokens in the bounding boxes and in the pixel level masks. And so this opens up, as I said, a tremendous amount of modeling possibilities that typically isn't available at this scale. And with that, I will say thank you. And if you would like, certainly feel free to reach out to me. My email is quinn.lathrop@pearson.com. Please check out the open source data set, which the URL is here, as well as a QR code. And then if you're interested about learning more about AI products and solutions, specifically in Poznan, please go to aipearson.pl, and this QR code will send you to that. So with that, thank you, and I'd be happy to take any questions live. Thanks.
Thank you, Quinn, for your inspiring presentation. So let's start with the questions. And we don't have any questions from the audience, so I will ask the questions. So the first question is, what are some of the most surprising findings that you observed after you launched the ADA calculus in production? What was there something that especially surprised you? Because there probably were some user behaviors that you didn't expect beforehand. So
yeah, definitely. Probably the most interesting piece is that the app itself is designed to help students that are struggling, which means we don't often see the best students doing their highest quality work, but we enter the students' normal flow of work when they're in a time of need. Where that translates into the modeling or questions that we need to think about very deeply is a large percentage of the images that students take are not high quality, or they are not following directions. And so it's a very difficult problem to think through of how do you still encourage the student to have a meaningful experience and a successful experience in their app, in their time of need, even when they're taking pictures of their keyboard or taking pictures of like their online homework system directly. And so how we compensate for the desired use case versus the use case that the students and the learners are trying to use the app for is an interesting tension that plays into how the models work as well.
Okay, cool, thank you. And another question would be, you mentioned those colorful artifacts that we see in all the pictures of computer screen, and I have a question, how long did it take you to include these colorful artifacts that you showed us within your data generation pipeline?
Yeah, so that's more of an abstracted example because the product use case is that it is not a cheating app. And so the encouragement from the product is write down, try to solve it, and then we'll be there to help you. And so in the use case, we don't want students even taking pictures of homework on screens. We noticed it within the first few weeks that this was a pattern, but then we can use more of the user experience and cues in the actual UI to shift students away from that use case and to try to encourage them to not use it to solve their homework, but use it to help them through a problem that they're having on paper.
Okay, thank you. And we have one question from the audience.
Great.
And the question is, how many actual users of the system you have, if not confidential? Are there mostly high school students or university students?
Yeah, so the actual numbers I can't give, but in the United States, calculus is typically taught at a college level, and so typically this is first, second year university. One of the challenges, especially in the United States, is that calculus and calculus 1 is one of the gatekeeping courses. And so if you want to go into nursing, if you want to go into any science or technology field, you have to pass calculus. And that's where we see a lot of students drop out and change their major when they fail calculus. And so that is one of the motivations for targeting that specific course and that demographic. But I apologize, I can't share the internal usage details.
Okay, it's understandable perfectly. We have another question from the audience, and the question is, as I understand, you largely generated the data yourself. Did you start by having a model generated from user popular datasets, and you went with this mindset from the start, or did you collect it?
Yeah, so like any R&D project, we went through several iterations before arriving at this strategy. And really kind of the key indicators that led us to the strategy was that we were chasing a moving target. The requirements kept iterating as I think any new product does, but we quickly found ourselves where if we started a data collection effort and spent money on it and spent time on it, we quickly realized that it wasn't going to satisfy the new requirements. And so then we went back to the whiteboard and said, well, what can we do? Can we use existing image augmentations? Well, that doesn't work because we need completely new expressions and we didn't collect certain tokens in the first round. So we needed more control over the process, which really led to the strategy of developing the generation capability. But certainly there's an aspect to it that requires inputs from actual humans, or a feedback loop from the data we're getting in from the application.
Okay, so another question from the audience: do the students cooperate with writing clean equations?
Luckily, we think that we've gotten to a point where we can generate messy enough handwriting to cover the majority of students. But that question is spot on, in large part because setting up the problem and knowing how to go from the textbook to start working the problem on paper, that is a very difficult task. And so if you have a student that doesn't even know how to do that, doesn't even know how to properly form a solution to a derivative problem, for example, yes, it's very difficult to understand what they're trying to do, as it would be if a teacher saw it and had no idea what the student was trying to do either.
Okay, so I may have just one more question from myself. That would be, well, since you have the experience in processing handwritten expressions, do you maybe plan to launch something like Ada Grammar in the future as well?
My group is primarily focused on the calculus app and the different capabilities of it. The larger group as a whole certainly has expertise in natural language processing and English language, and so while there's nothing specific to announce, we will continue to produce products that support learners and both expanding the scope and not just in calculus, as well as supporting a larger audience throughout the world.
Okay, cool. So we have another question, but I guess this classifies under a kind of private question, because one user asked, can I use your generator for a different type of data, for example, sign language?
Well, so what has been open sourced is a data set that came from this capability. The capability itself can be dramatically changed as needed to support certain use cases. And so for example, the Kaggle data set focuses specifically on the topic of limits in calculus, which is a major area that's taught in the United States in Calculus 1. But if instead you want to focus the target on some other part of math or some other even area that you can represent in the core pieces. So for example, if you can write LaTeX, you can generate these images. And so for sign language, I don't know. I haven't thought about it. I think that's an interesting idea, but that would be going back to the same core principle of developers have control of this capability. They can tweak it to match the use case that they would like to model.
Okay, so we've got a very, very hot Q&A section, because we've got another question from the audience.
Great.
And this is, decoding single equation is one level of challenge, but how about understanding the whole math reasoning? Oh,
yeah. Yeah, absolutely. And I would encourage you, if you can, to use the Ada Calculus app. So we use OCR, or the handwriting recognition, in order to bring in the input from the student. An alternative way to do that would be to do it through a keyboard, and there's a keyboard in the app as well. From that point on, it goes to another capability which tries to determine what the student is doing, what is their intention of this equation, which is a really difficult challenge. And if you flip through any math textbook, one thing that is shocking that you might not notice as a student is so much of the math is communicated in words. And so how, as a mobile app, do we get that natural language when our input is primarily equations is a very challenging and interesting problem. But this capability identifies the intent of the student, marks whether each step of their solution is correct or incorrect. And then again, if it identifies something that the student did wrong or went off path, that's where we focus personalized remediation.
Yeah, cool. I guess we're done with the questions from the audience. So Quinn, if you have anything to add to our audience, so you can just go on and say it now.
Great. Well, I just want to say thank you. I think this was a great experience, and it was a pleasure to be a part of. And thank you, and thanks to all the organizers. Appreciate all the Q&A. If you're interested, check out the data set on Kaggle, as well as check out Pearson and check out the Ada app as well. And thank you.
Thank you, Quinn. Thank you for your talk.